Good evening, everyone. I would like to welcome you all to the second of this week's Sliver lecture series. To proceed with our theme of discovering the elastic boundaries of architecture and architecture culture, we will continue to visit the multidisciplinary edges of our profession tonight. We will be taking quite a pressing, practical, yet curiously speculative and controversial term in terms of subject matter, I would say. Sustainability. Even though for many of us architects, sustainability has become a staple concern for pressing environmental reasons, there's a wide range of approaches on how architects use building techniques to recalibrate the moral compass of the profession. And that's when people like Thomas Auer, tonight's lecturer, come into play to guide us. Trained as a process engineer at the Technical University in Stuttgart, Thomas is a partner and managing director of Transsolar, a German engineering firm specializing in energy-efficient building design and environmental quality with offices in Stuttgart, Munich, and New York. Outside of Transsolar, Thomas has been teaching at Yale University and was a visiting professor at the SA in Paris and other universities worldwide. He speaks frequently at conferences and symposia. In 2010, Thomas received the Tree Hugger Best of Green Award as the best engineer. Thomas is one of the few pioneers of integrating sustainable engineering techniques into architecture. Because him and his company really is the best of the best, world-renowned architects and artists are all lined up to collaborate with him on projects and competitions. Thomas has this incredible ability and competence to integrate energy, climate design and engineering ideas and principles into architectural concepts so fluidly. It is a rare occurrence to find a consultant with such a sophisticated understanding of architectural design. Therefore, his work always enhances and complements the provocative concepts of many of the radical architects he works with. Majority of the energy design techniques that are so commonplace right now are either direct results or byproducts of Thomas's collaborative and experimental research. It is no surprise that Gehry, Novell, Foster, Sejima, OMA, Graham Koolhaas, Stephen Hall, and many of the other architects at the forefront of our profession and their clients choose to work with him repeatedly. He has been involved in artistic endeavors such as his collaborative cloudscape installation at the Venice Biennale. His work is a constant reminder, therefore, to us that science, unlike popular bias, is an unpredictable yet messy territory that requires a rigorous experimental, strategic, and also creative approach. If there's such a thing as an avant-garde engineer, I would say Thomas would be it. Thomas is certainly one of the leading voices of such an important concern for us as architects, and it is my pleasure to host him, my former teacher, here at the Angewandte tonight. Ladies and gentlemen, Thomas Auer.
Thank you for this nice introduction. I hope I can catch up. There's just one thing where I would like to change your wording. It's not me. It's like Transsolar is not a one-man show. It's an office with 50 people. And there's many smart people who contribute to our, I think, pretty successful work so far. Okay, so let me talk a little bit about our work, and it has a lot to do with the environmental issues we are facing. And I like to show always this image, and you all have seen it already, the positive proof of global warming. The funny thing was when I showed this in Italy, the first question was, how does 2020 look like? Something I haven't thought about before. But there's still, let's say, there's still people who question global warming, and particularly you see a lot of this in the US. And the interesting thing is that 99% of all scientists working in this field has no doubt that there is something like global warming. The question is what's going to happen. And I think there are many, we can discuss this forever, and there are many predictions, and all of them are probably wrong. But we know that the climate is going to change, and the question is, like, how do we deal with it? And what do we do? And there is a lot of pressure coming onto the building sector. And this means, like, basically we have to reduce our energy consumption. or carbon emissions from buildings, basically down to zero. The European Union has established the carbon roadmap 2050, which is required to become legal legislation in each country in the European Union, which basically says that carbon emissions from the existing building stock has to be reduced to 10% of today, so by 2050. And honestly, like working in this field for the last 20 years almost, I have no idea how we can achieve this. But that's what politicians sometimes do. They put goals so far into the future that it doesn't require any immediate reaction. But however, this is the goal, and given the European debt crisis, other things became focus these days. But this is the goal, and so far it has to become legal, or it has to become legislation in each country. So how do we get there? I think that's the most important question. And how do we get there in a way so that we live in a world we still want to live in? I love to show this because this is a spa in Tokyo. We found this in a magazine, and the advertisement said, "Welcome to breathtaking Tokyo Water Park, where you can wash away the pressure and stress of the overcrowded city." But I think the interesting thing is we haven't worked on this spa. But no matter how much energy they use, the energy consumption per person is negligible. And whenever we talk about energy efficient building design, we tend to talk about kilowatt hours per square meter per year, or kilobtu per square foot per year. But how many people really use the building? Do the people really like the building? So this makes it obvious that we cannot disconnect energy performance sustainability from architectural quality, from environmental quality in the place. Like we can do a zero energy building if nobody's using it. It's a waste of resources. So it's always connected, and it's an obligation. Sustainability is an obligation which you cannot hand over to some crazy engineer sitting somewhere who adds something to your building which makes it smart. It's something that has to be part of the design, and some people contribute to it. We are just one of the people contributing to it. And what we do, we call climate engineering. And most people think it's pretty new. Some people also call it climate design or energy design. I think it doesn't matter. We started to call it climate engineering when we started Transsolar in '92. And it's not brand new. Like we found this spa in Rome, built 109 after Domini. And there was people questioning the orientation of the building, and they figured out that this is the one orientation that gives maximized exposure to the sun for the people using the spa while protecting against the cold wind. So it was pretty smart for the time. There was no modeling involved. People were just smart about it. Now, this is what we do. So like 2,000 years, almost 2,000 years later, we do the same thing. And like I mentioned before, we were invited to do this installation at the Architecture Biennale, the last Architecture Biennale in Venice. And when Sejima asked us if we want to do something, first of all, we were super proud because being the first engineer that can have an installation at the Architecture Biennale is something special. But at the same time, we said, like, we are doing, well, the stuff we are doing is invisible. We are doing warm or cold air. But how can we do something that becomes feasible? And we did a cloud before, a couple of years ago, and we said, why don't we do a cloud again? Because a cloud is basically the visualization of climate engineering. And I think this is what it is. And we made this image here that illustrates how the cloud works, and it's basically just 3 layers. You have a bottom layer where you have something like 20 degrees, moderate relative humidity where people are, and then if air gets warm and if air gets humid, it goes up, it has a lower density. So the cloud layer has to be separated so that the cloud appears, so that you can have water particles in air without getting evaporation. So you need to have this saturated layer, which is slightly warmer, so that it floats on the bottom layer. But then, if this layer is touching the ceiling, you get condensation right away when the cloud is gone. So you need to have a hot layer on top, which is even lighter, that keeps the cloud, avoids that the cloud starts to touch the ceiling. So that's what it is. So the theory is pretty simple. It took us something like half a year of experimentation to get it realized, but it's all about air movement and how do you create a situation where you have these three stable layers. But then, this is how it looked like. Oh, one image is gone, sorry. So there was an image from below the cloud, and there is a ramp, and people could walk through the ramp, over the ramp, through the cloud layers, and experience the three different layers. Unfortunately, the image is gone. But then they came up on top of the cloud, saw the cloud from above. So it was really this floating cloud. It was clear below, it was clear above. And people could really experience what it means to have to walk through 40 degrees, 100% humidity in a time when it was already super hot in Venice. People got a really good understanding of what adaptive comfort means, because getting down to 30 degrees became suddenly super comfortable. So this is basically what we are doing. Not clouds, like climate engineering. And what does this mean with regard to building design? I think we see a lot of this we see these days when people talk about sustainability. They take something which is stupid to begin with and add gadgets to it. And unfortunately we see it a lot. And all these kind of checklists like LEED, like BREEAM, and we have the German one which is called DGNB, they actually reinforce this kind of approach. And there's nothing wrong with the checklist. I think it's probably important. LEED has created momentum with regard to sustainable building design. I think it's a huge story of success. However, it's our responsibility as designers not to do something like this. We have to attack the thing and not add gadgets to it. So what we have to do, we have to come up with something that starts to become much more efficient by design. And I think this is what interests us as engineers, is this interface between design and engineering. Like, we are engineers. Also, when we worked on the Biennale, we said we want to do this together with an architect. Like, we don't want to give people the impression that we want to become architects. So we worked with Tetsuo Kondo from Japan, who designed the space, who designed the ramp, and we did the engineering for the cloud. So, but we love to work on this interface and to challenge the design. If we look back in architecture history, this is a picture from 1920 from the Flatiron Building in New York City, and it was built in 1902. And what you see is that every single window is operable for natural ventilation. Every single window has external shading, and the floor plate is limited, you see at this building, so that people are really lined up along the facade, and people have really access to fresh air and to light. And the reason was pretty simple, because Carrier invented air conditioning in the 20s, so none of these buildings at the time had air conditioning, and designers knew what they have to do to make the best out of it. I don't want to say it was always super comfortable, but it was probably comfortable 11 months a year, and not when it was like 100% humid in New York City in August. However, all of a sudden we had air conditioning and architecture became like this. And without judging the aesthetics, if you look at this tower, there's so much coating that it's a glass tower, but people don't even get light. There is no window, it's operable, and if there is a power failure in New York City, or power outage, people have to leave this building. They can't even survive in this building. People can still stay in the Flatiron Building built more than 100 years ago. So the Flatiron Building provides better environmental conditions, better energy performance than this building. So what happened? I think it's this thinking about 1 or 0. Either we go fully passive, or if we have air conditioning, who cares? And this is the kind of thinking that all of a sudden happened. And like what we think is not that we think we have to go back to the Flatiron design. I think we have to apply the physics and the understanding of of this interaction between inside and outside into contemporary architecture. Like this is one building which I'm going to show later a little bit, where we have this breezing facade in a cold climate in Canada. And then this is a building Danish did in Hamburg, which is Unilever, where they used the first time a single layer ETFE foil to create a buffer zone so that in this windy condition of Hamburg, they could have an external shading which is protected against the wind. And it's also like they get air into this cavity from the courtyard. And once in a while, there's the cruise ship terminal is about a block away. And when these cruise ships come, they have basically smog conditions in Hamburg. People have to close their windows because there is no exhaust air treatment in these cruise ships. So these people can still open the window and have natural ventilation because the air doesn't come from outside, it comes from the courtyard into the cavity. So, you know, what we see is like, there is an implication that comes by design. So design is actually key to have a change. Of course, we can have a big air conditioner sitting in the basement, supplying mechanical ventilation to the space, but people appreciate if they have an individual control over their environment. People appreciate if they can open a window, if they can control the amount of light, if they can control the shade. And if they are appreciated, they also perform better. And I think this is what we see a lot of research in the US, where institutes look at productivity of people if they have daylight in their working environment. And it has a significant impact. So what we see is that design is key in order to get progress to, let's say, better performing and higher quality architecture. But then at the same time, we know that about 98% of our buildings worldwide are designed without architects. Or we have to be more precise. They are designed without architecture firms. So there are builders, they have hired architects who do some of their design, but it's not an independent design firm who is working on these buildings. This is like a suburb of Toronto. So I think so we have this challenge of becoming carbon neutral in considering the entire building stock, considering all new buildings. We know that with design we can have a big impact, we can really have a big effect on the performance and the quality of the environment. At the same time, as architects and engineers, we do not have really access to the market. And I think this is what we need to face. This is what we need to consider. And I think we have to be smart with the kind of buildings we do to prove to the people that we do have solutions to offer. This is an urban design we worked on for Mustard City with Foster's, which is supposed to be the first city for 60,000 people in Abu Dhabi being completely carbon neutral. And you think like, does it make sense to build a city for 60,000 people in the middle of the desert, in the middle of nowhere? I'm not sure if it makes sense. However, for us it was a really interesting task because we did all the studies, the energy balance on this urban development, and we said, if it's possible in Abu Dhabi, in this unbearable, severe climate, then it's possible everywhere. So we did the study, and this was basically the result. This would be a conventional city in this kind of climate, emitting something like 1.7 million tons of CO2 per year. And this is the design of Mustard City, taking mobility, taking waste, taking everything into account. What you as architects need to look at is like the buildings contribute something like 56% to the overall balance. So the biggest single contribution is coming from the buildings. Like all the renewable energy sources which supply 100% of the power and the energy required, contribute only 24% to the overall balance, but the buildings contribute 56%. In order to achieve this, we did all the modeling for we didn't design the buildings, it was just a master plan, but we designed kind of prototypical buildings with Fosters for different building typologies, and this is what we ended up with. In order to get there, the buildings need to be on average about 80% more energy efficient than compared to what they do today in Abu Dhabi. 80%. And this is a pretty significant design task. It's like you need to know every kilowatt hour that goes into your building by name, basically. So you think like something like this is basically history. It's never going to happen again. Moshe Safdie, his Habitat 67 in Montreal. And you look at this and you think like this is the kind of beauty which is gone for the future. It's actually not really true. Like you look at this is a passive house. We didn't work on this. It's Key Architect. It's in Japan. But I think it's a reasonable solution for the problems or for the challenge. But it's actually not necessarily our approach. Because in order to get to this passive house standard, you really need to minimize the amount of fenestration ratio. So you start to compromise the quality of light, you start to compromise the environmental quality. You do not zone your buildings for different temperatures. It's not a passive system. Like a passive house has nothing to do with passive design. I'm not sure why it's really called passive house. I think this is something we have to be aware of. And we worked on this, which is the Atskelion building with Herzog Timuron. And you think like, this is stupid, but this building passed the really restrictive Swiss code, Swiss energy code. And what you figure out, given the amount of insulation we use these days in our materials, the kind of material we use, the energy losses through the envelope is about 10% of the overall energy consumption of a building. The biggest single energy consumer in a commercial building is artificial lighting. So if you get the task, let's say as an architect, you get the task to design a building that covers an entire block, and you have to maximize the massing that goes on this block, but you want to make sure that everybody has access to daylight. You actually might end up with a solution like this. So I think that's the beauty of what we are facing, given the materials we have, given the computer tools for modeling we have. We could really end up with something like this. And we could actually even optimize it with parametric design to get really to really achieve the goals we established at the beginning of a process. So it's not that every building in the future has to look like a passive house. It's not the case. I think we just have to be creative and smart. And this is what we do. We support these design processes with modeling. And just for fun, basically, I show you this. This was one of the first CFD modelings we did for this glass entrance hall of a Danish building in Lübeck, where there's this glass solar chimney on top. And the idea is that there is a ground duct, and the glass solar chimney pulls the air through the ground duct and cools the space. And then the air goes up, the hot air goes up, and will be exhausted naturally. And we did the CFD modeling to prove that it's working. And this is when we showed this colorful diagram, the client immediately believed us. As a matter of fact, looking at it almost 20 years later or 15 years later, it's complete nonsense, you know. And air would never create this kind of plume of cold air. It would actually establish a cold layer at the bottom, and therefore would actually work much better. But this was the beginning of modeling, and this is something I don't want to tell you in detail what it is, but this is how it looks today. It became so sophisticated, and we actually see the limits of profiles where this is like looking at downdraft of cold air in a cold climate in Canada. And to what extent do we compromise at a minus 30 degrees outside the indoor environment with cold air that comes down a glass facade. And we can say, okay, up to a meter, we compromise it if we have minus 20 degrees. So it became this sophisticated over the past 15 years, and we can really use it as a design tool to inform the design of buildings. So let me show you this high-rise building we worked on. It's in Canada, in Winnipeg, and it's for Manitoba Hydro, and we worked with KPMG architects from Toronto. And like when I describe you what the climate in Winnipeg is about, they have about 2 months with temperatures of minus 35 degrees. And here, this image shows somebody throwing boiling water into the air, and it's freezing instantaneously. This is what it is about. I got there for the interview in January, and I got out of the airport, and I thought, you know, oh my God, a cold blast hit me. I jumped in a cab, and I said to the cab driver, oh, this is really cold here. And he said, you think this is cold? We just got a heat wave. So then you know what the place is about. It's always useful to ask cab drivers for the climate. They're really experienced with climate conditions. So, but when we talk to the people, they always said, but you know, it's a cold place. But when it's cold, it's always sunny. And we looked into it, and we found that Winnipeg has more solar radiation than the city of Milan, for instance. They have on a vertical facade, they have more solar radiation than any other cold city worldwide. And we said, okay, this is a big potential. And we said, there is a place to do passive solar design. It's actually Winnipeg. It's not some people in the 70s, they did passive solar design in Arizona and New Mexico. I don't think that this is the right place. Winnipeg is the right place. So we ended up, after a pretty long schematic design process, we ended up with this design, and this is just showing a cross-section through the building. And what we do in winter, we use this south-facing 6-story winter gardens as an air supply unit. Sorry, like you always see these diagrams with cold and warm arrows that go into a building. This is what we are doing, basically. So I have to bother you with these kind of diagrams, because it's the essence of our work. We do not design the buildings, we design the arrows. So the air enters the building in winter, and then there are units in these 6-story winter gardens that heat the air up to 10 degrees. So we keep the temperature in these winter gardens at 10 degrees, and when the sun comes out, it further heat up the winter garden. And then there are these decentralized units that take the air from the winter garden and supply it into a raised floor plenum that distributes it into the depth of the floor plate. And then the air is going down this exhaust chimney into the basement, where there is a heat recovery unit that transfers the heat from the exhaust to a water pipe that brings it back to the supply unit. So it's pretty straightforward, pretty simple. And then in addition for heating, there is plastic tubing in the concrete slab so that the structure itself provides radiant heating and in summer cooling. And so in summer, the winter garden is just open. It's basically an outdoor terrace. And then the units, they cool down the air before they supply it to the raised floor plenum. And then we exhaust naturally by this solar chimney. And then in addition, we have about 300 boreholes, like geothermal boreholes, under the building. So you drill down about 120 meters. You put in a water tube, a closed loop water tube, you pour concrete on top, and then you create a heat exchange with the ground. And then this heat exchange provides 100% cooling required for the building and about 50% of the heat. So this is how it looks like. This is basically, the building has no air handling room, no mechanical room for air handling units. You still have a penthouse where they have the boilers and the electrical rooms and IT rooms, but there is no mechanical room for air handling units. This is basically the 6-story winter gardens, which is the mechanical room of the building. The mechanical units are integrated in this bench, and they supply the air into the space, and then behind these panels are the decentralized unit distributed into the depth of the floor plate. And this is what it is, and people like the space so much so that they even use it for yoga classes, but then they close the shade not to be seen from the street. And then this is close to the solar chimney. Here is the air intake into the solar chimney, and you look down onto the podium with the green roof. And you think, what does it mean in terms of energy efficiency? And like, this is a comparison, average Canadian commercial buildings these days, and then new commercial buildings. This is the latest energy code in Canada, and then this is a kind of system where you've got an incentive for energy efficient building design from the government at the time when we designed the buildings. This is where we ended up with. And given the extreme cold conditions of Winnipeg, it's actually a pretty good number. It would even be compared to buildings in Germany or Austria or Switzerland, like Central Europe. This would be still a really good number. And so for this kind of climate, it's actually really good. Really, really good. Whatever it means. But I think this is interesting, and the funny thing is, we really get a lot of pressure because of this building from the Canadian engineering community, and then you got the impression that the people feel threatened. And the reason is pretty simple, because like they had two paradigms for energy efficient building design for commercial buildings. One was the less cost, the better. And the second was the bigger floor plate, the better, because you minimize envelope. And we did the opposite and proved it wrong. So 60 years of research in energy efficient building design was proven wrong with this one building. But it's just a different approach. Of course, you can also do a very efficient building with a deep floor plate, and you minimize the amount of glass, like the passive house. It's just a different model. And I think it's good that we have various models we can use and apply and give clients different opportunities or possibilities. But the other thing is also, when we do a building like this, we have an impact on the local microclimate. And like you see here, when wind hits a building, it goes around these buildings in all directions, but there's also one component which is going down, and it hits the ground of the plaza of the building, and it creates super uncomfortable environment down here. And we tested a lot, and at the end of the day, it was this simple canopy which redirects this downdraft straight to the neighbor before it hits the ground. But the neighbor doesn't have operable windows, so he doesn't care. No, it was this simple canopy which was basically the solution. And again, this shows us it's not rocket science what we are doing. It's just important to consider these issues. And here you see the plaza. And this was an event. They don't have always this amount of people on the plaza, but at this event, people at least enjoyed the plaza. And like, this is the solar chimney of the building. And of course, we love if something like the features we propose for a building design becomes the icon. But it's really that the solar chimney became the icon of the building. So the building won several awards, became the best building of the Americas 2 years ago, etc., etc. But we still discuss with and what's very important, we still monitor the building, and we exceeded the energy model. We exceeded the modeling, so we modeled 88 kilowatt hours. The last year we measured 85 kilowatt hours, and the number continues to go down. So we actually proved that the modeling is not wrong. Talking a little bit about wind. This is actually, we have a building where we use the wind turbine on top of the building, which is not used very much in publications. fortunately. I found this in St. Louis when I was in St. Louis 2 weeks ago. And you see these wind turbines being at the edge of the building. You know, a building is creating a wind shadow. And these wind turbines are exactly within the wind shadow. So by definition, they are not doing anything. And I thought, this is so stupid. I have to make a picture. I'm not sure who was the engineer. It was not the architect's fault. He might not have known that there is a wind shade at this location. But I think there are smarter ways how we can use wind in building design. I want to show you this high-rise building, small high-rise building. We worked on the Sauer Hutton in Frankfurt for a bank in Germany, which is called KfW. And like, if you look at the shape of the tower, it's like an aircraft wing. And this is the windows of downtown Frankfurt. You see that it's like an aircraft wing that is within the prevailing wind conditions of downtown Frankfurt. So we thought, how could we use this for the operation to the benefit of the building? And we ended up with a solution where we have a double facade, which we use as an enclosed corridor. And like if wind comes from here, which is mostly the case in intermediate season, we open up the facade on this southwest facing corner and keep the remaining outer facade rather closed. So we create an even overpressure in this double facade ring that is enhancing natural ventilation. But it also, it's increasing the times when we can have natural ventilation to something like 70% of the year. But what it's also doing in a tower, when wind comes from here, you have overpressure here, you have underpressure here. Now if the people keep their windows tilted, you get this cross ventilation, which can cause an energy consumption in intermediate season, which is completely unnecessary. So with this pressurized ring, we get even pressure conditions along the inner facade, and we actually minimize this cross ventilation at the same time. So these are the two effects we create with this double facade. And you see like the outer facade is designed like gills of a fish that really catch the wind. So the entire building is basically a big wind catcher for natural ventilation. And here you see all the old purples that can be used for natural ventilation. And let's say even to the extent where you start to question whether the building has any mechanical ventilation at all. But you should not forget, like we designed this building before the bank crisis. And it's a bank building, and bank employees, they have this specific requirement that there can't be an hour a year where the space is not comfortable. So there has to be a switch where they can say, I want to have 24 degrees. I don't want to say that people expect this, but the people are used to this kind of comfort. And it's difficult to convince them of anything else. But still, like there's now 70% of the year the mechanical system is really turned off. And so we do have the use of the double facade to enhance the energy performance. But these are all these kind of corporate buildings, and I like to show this one, which is the French school in Damascus, which is absolutely low budget, super simple, where we use these solar chimneys. We worked on this with a French architecture firm called Atelier Lyon from Paris. And it had to be a super low budget construction because it's completely paid by the Parents Association. And these parents, they are all European, so they are used to be in spaces, or they are not used to be in spaces with air conditioning. So the parents came and said, could you design a building without air conditioning in Damascus? Because air conditioning is making our kids sick. And we thought, okay, it's Damascus, it's not Paris. But we thought it's an interesting challenge, let's give it a try. So we ended up with these solar chimneys facing west. So when the low sun ends in the sun afternoon, they hit the solar chimney, and this back wall is a masonry black painted wall, and the wall absorbs the heat and it stays hot at night. And Damascus cools down at night quite significantly. So then it pulls the cold air from these courtyards through pipes which are embedded in the ground slab into the classroom and then out through the solar chimney, and therefore cools down the thermal mass of the building to provide good conditions the next day. We did the modeling, we showed them that in June, when they have like 40 degrees every day, the spaces heat up to something like 30 degrees at the end of the day. But the parents said, 30 degrees, if we have 40 outside, 30 at the end of the day, that's okay. And we did it, and it works to the extent that they want to do an extension to the school and want to continue the same principle. And there is nothing motorized. Like the courtyards where they have vegetation and the shade, they have to pull over the shade, and they pull it over in April, and it stays there until the end of September. All the flaps inside are operated by the kids. There's nothing motorized. And if they don't operate it, it just gets hot. I think it's quite simple. But it was really low budget. It was probably the least expensive building we ever worked on. And I think I love to show this because you see it's not sustainability issues which drives up the budget of our buildings. It's our expectations. It's like the expectation that there is a switch and we can have air conditioning if it gets slightly too warm. It's this level of expectation which really makes our buildings so expensive. Geometries. And even to the extent that it can inform advanced geometries to a certain extent and makes them more meaningful. And just at the end, I want to show you some work we've done in the outdoor environment, because I think that's the next thing we have to really be careful or think about. This is a picture of downtown Paris, and we all know what happened in the summer of 2003 when we suddenly got the heat wave, and where thousands of people died, in particular in Paris, because there's so much heat, solar heat, that is absorbed in an environment like this and stored that the city doesn't cool down anymore. And none of the buildings have air conditioning here. So if the city doesn't cool down, the buildings don't cool down. And I saw measurements done by Météo de France which showed that the downtown Paris in the summer 2003 was only 1 degree warmer than the outside of Paris during the peak day conditions. But during the night it stayed 10 degrees warmer. So while the outside of Paris cooled down to 20 degrees, downtown Paris stayed at 30 degrees. And then the buildings, they cannot cool down if they have a minimum temperature of 30 degrees outside. They get warmer and warmer to the extent where elderly people get into trouble. Now, this is all man-made. You see this picture is from Foster showing a street in Dubai. And what you see is having 39 degrees outside, the radiant temperature that comes from the ground and the surface of the building is actually 52 plus the sun. So the perceived temperature, which you can calculate in an outdoor environment, is probably something like 70, 80 degrees in this environment. This is all man-made, so on top of this severe climate, we make it worse, where all of a sudden you have no chance than going into an air-conditioned shopping mall or to go skiing in Dubai, becoming the only way to survive. So this is how we calculate outdoor environment, and with this perceived temperature, taking all the parameters, it's like 7 parameters, which are like air temperature, radiant temperature, solar, like long wave and short wave radiation, humidity, air movement, but then also Kelvin factor into account, and metabolic rate of people. And the goal is in hot climates to really get into a range which is here, which is yellow. This is actually green, it becomes almost yellow. And getting out of this extreme heat stress situation. And you think, does it make sense? And somebody from Transsolar took this picture in Kuala Lumpur, and it shows that people in this outdoor cafe sitting beyond the canopy where they're in the shade, and they have these fans, and they're blowing water in this already superhuman environment. And I think, why the hell they are doing it? But when you do the PT calculation, you see they get a little bit of cooling. They get something like 3-4 degrees of this evaporation in combination with the air movement, in combination with the shade of the canopy. People feel happy enough to sit here in the shade. And then he also did a picture from inside where it was super air conditioned, probably 18 degrees. There was nobody inside. Everybody was sitting here in this 35 super humid environment. So you recognize that people in the outdoor environment accept a much wider temperature and humidity range than they would ever accept in an indoor environment. And I think this is what we have to use, given the issues of global warming in our cities, but also working in hot cities and cold cities. We did this study for Doha, and showing for the summer month, if somebody is exposed to the sun, you have basically 100% of the time you have extreme heat stress. If you give him a shade, extreme heat stress going down to something like 60% of the time. If you have shade and air movement, it's about a third of the time. And then if you have some radiant cooling, which you can do by a water surface or by a tree, or even if you cool a specific location a little bit, then you want to block the hot wind, because then the hot wind suddenly becomes like a hairdryer that blows on you, this 45-degree hot air. And then you see the extreme heat stress is going down to something like 10%, 10-15%. So this is what you can do even in this unbearable condition of Doha. So we worked with lava architects on the outdoor plaza of the competition for this project in Mustard City, and the Mustard Plaza they call it, and where we ended up with these umbrellas that provide the shade. And here you see an image of these umbrellas, and here from below, like renderings done by lava architects. But the intention was to really program the outdoor environment and to have this transition from coming from this unbearable condition to this super cool indoor environments, having this transition zone that goes through the outdoor, and then having the shade during the day with PD on top, with low coating on the bottom to avoid long wave radiation, all these high-tech applications, but then at the night to fold it so that the plaza can really radiate to the space. Like you get a lot of cooling at nighttime if a place can radiate to the space. So we looked at the numbers and we showed, I don't have it here, but we showed that this folding umbrellas have a big impact on the conditions. And finally, I want to speed up. Finally, I want to show you what this could mean in a cold climate. Like we worked on a competition with big architects in Helsinki for this piece of land, and the master plan was already established, and this was the master plan we got. And the competition was only for one building, for Citra, it's called From Low to No. But Citra encouraged all the teams to also think about the master plan if necessary. And we looked at it and we said, like with big architects, this is basically what we could do in terms of massing. But if you do this, none of the neighbors have access to sun, which we thought is the most important thing in a climate like Helsinki. We said, why don't we cut it with certain angles depending on orientation, and then apply this to all buildings. And we did the modeling that showed that we get 2 to 3 times more sun hours, especially in the intermediate season, into the public realm. And then we said, but we can't cut out so much massing of the master plan. And we said, but there are areas where there's more distance, where you can have more massing. And so this was finally the proposal we submitted in the competition. And I think when the jury saw this, this was the moment when we lost this competition. I heard somebody from the jury saying, city planner, when he saw this, he said, if we even discuss this, I'm out here. But the intent was not that the city has to look like this. The intent was to say, why don't we give people a three-dimensional shell in which they can design their buildings and not just a plot? So they did this example where they said, okay, this is the shell. These are all the buildings which could be designed within the shell. And they did many more just as an example of massing possibilities that could go into the shell. However, they didn't like it, but the one thing I want to show you finally is there was the goal that the entire neighborhood becomes carbon neutral at the end of the day. And we said, okay, first we have to approach the passive design of the buildings, and then we need to think about service strategy, and then we need to think about where the energy comes from in this line and not any other, let's say, priority. And we ended up with this kind of energy supply scheme, which I don't want to talk to you in detail, but I think in the future there will not be one energy source which is serving whatever we need. We need to have smart grids. Our buildings need to become smart in terms of energy consumption, but they also have to become energy producer, and they all need to talk to each other. And we're going to have several energy sources. And what we found there, they have also this ferry terminal just basically a block away from the site. And we looked at how many ferries leave from the site to other places in the Baltic Sea. And we looked at how efficient do these ferries operate. And these ferries operate at an efficiency of something like 20%. 80% of the energy is becoming heat that goes into the ocean. That's what it is. Actually, a car operates at an efficiency in average of something like 10%. This is how we use our energy. And if we take into account that we move a ton of mass in order to get a person with less than 100 kilos from A to B, it's actually an efficiency of 1%. So we looked at what if we put a container with phase change material onto these ferries, and we, instead of putting the heat into the ocean, we put the heat into these containers. And these containers, they actually exist. You can rent them in the city of Frankfurt for temporary heating. And they get loaded by some manufacturers who have waste heat from their manufacturing. So they exist, and we said, if we put these containers on the ferry terminals, they come back and have all the heat stored in the containers, and we can feed it into the urban development. And we did the calculation, and we showed that these containers alone can provide 100% of the heating demand necessary for the entire district. So this is where I think where we have to become really smart and looking for synergies and opportunities. And this is how I sometimes think about when I see all these different approaches about energy efficient design. This is an image a Transsolar guy took in the subway in New York, where they say keep to the right, but the arrow goes to the left. This is how I sometimes feel, giving people directions. Thank you very much.
Questions? There's got to be some questions.
Yes?
Why was the urban designer so afraid of having this max envelope system? Because they look like picture architecture?
I think the problem was, and we didn't know this, going through a master plan application process took them about 10 years. And they just finished the process. And then we came and said, by the way, I think it was more a process issue than anything else. But we said, we knew that other teams proposed a completely different master plan. Like Rex from New York, they took it all out and put some high-rise buildings in there. And we said, let's not gonna do this because they're gonna kick us out if we do this. Let's try to massage the master plan. But even the massaging was just too much in terms of process.
airport. I saw a picture at the master project, something about keeping it neutral, and there was a title there with carbon offset schemes. I think I read. What does that mean? They have carbon trading schemes to do the city, or is everything inside of the city, or do they trade carbon, plant trees somewhere in the world? What do they do?
To be very honest, I don't know yet. At the time when we delivered the master plan and the energy concept with Foster, and it was a big team. It was a big team, many people involved. It was really, everything was designed so that 100% of the energy is generated on the side of the city. No offset, no carbon trading. But I know that they had some issues with the kind of stringent, let's say, sustainable design guidelines we put together for the buildings. Because they were pretty clear, and it means like none of the buildings could have an all-air, typical American all-air air conditioning system. It's just a no-go. And I know that they were concerned about the level of, let's say, stringency that goes into the design. And they might have watered it down to be honest, I don't know what the current status is.
What's your personal opinion about the notion of, getting to neutrality by trading carbon? Doing the project here, and then you have some other place in the world, and then you trade your carbon to make it.
To be honest, I think it's like the Americans would say BS, like bullshit. I think it's a little bit like, sorry for using this term. It's a little bit like in medieval times when people paid money to the Catholic Church when they have done something wrong. I think that's my personal opinion. I think it has a certain danger to it. And I think we should solve our issues in our countries. And ideally on our side, but no, I think it was at the same time, I think it's always, I think we can talk forever where we put the boundaries. This is a really difficult question, because if we put the boundaries of our calculations around the building site, things become ridiculous as well. Because on a city level, you have synergies. When one building, like a housing, you can have, if you cover a two-story raw house with photovoltaic, you have a surplus on energy that could be used in commercial buildings. In commercial buildings, you have waste heat, which could be used in housing. Like you have synergies on a city level that makes sense to think about energy efficiency beyond the single building. But I don't think that we should go beyond a country. Or maybe we should go, but in terms of, like in Norway, they have storage capacity for our hydropower. In the south of Europe, they have more solar power. So on this level, but not like paying money to New Zealand so that they plant trees. I think this doesn't make sense to me.
Thanks.
Yeah.
You raised the issue of seasonal storage. I also think that it's could be a very important strategy to solve our energy problems. And with heat, I think it's not such a problem. But do you think, on a more regional level, like in Norway or in the Alps, you can do hydropower and solar electricity? Are you working on systems or techniques which enable us to store electricity more locally?
There is we just did a submission for an Arctic research station where they have a lot of wind, obviously, but nothing else. So we proposed to use wind power, obviously, and energy storage became the biggest issue. So right now, there is a community there, it's in Canada, it's in the Canadian Arctic, and the entire community is the most unsustainable community I've ever seen. Like, they ship in potable water, and they have potable water tanks, and they come on a truck to every building. They take the sewage out on a truck of every building and put it in a lagoon where it's freezing. And then they have these diesel generators that generate power on a pretty inefficient level. Every building has its own small diesel generator for power failure, things like this. So anyway, long story, make a long story short, power and power storage is the biggest issue at the same time for these people up there. Power is super expensive. They pay 10 times more per kilowatt hour than people in Toronto pay or Winnipeg pay for power. So the question was, how could we store it? And what we found is there is this very promising technology which has been redeveloped, which is probably pretty old, but it has been redeveloped now, where you can take surplus power and turn it into methane, and then you have it as gas. And it's much easier to store gas than to store power. And then with a gas generator, you can get it back to power. And it's pretty efficient, actually, and you can decentralize it. I think that's the beauty. And it's an institute, coincidentally, in Stuttgart, which developed it. It's the ZSW, Zentrum für Solarenergie und Wasserstofftechnik, which developed it. And I know people there, I talked to them, and they said, like, you can scale it down to something like 1 or 2 megawatts. So you can really use it on a district level. And it's certainly the technology which potentially helps us, let's say, with all the wind energy, with all the solar energy we have now in Germany, to store it without having these huge requirements on infrastructure. And they can also do fuel. So with the process, they can decide whether they want to do gas, methane, or whether they want to do fuel. And they got approached by car manufacturers. So car manufacturers said, if we can do fuel, maybe we don't need to go all the way to do electric cars. Like if we can take our renewable energy and turn it into fuel, we could continue with the kind of cars we have. And now they got approached by an airline, because the airlines are under pressure with their CO2 emissions as well. And they said, if we can use wind power to generate the fuels that goes in our airplanes, you know, we are done. We don't need to pay for carbon trading. So it's pretty interesting. So this is where I see a lot of potential in the future. I think it's going to take them another 10 years before it's fully developed on a bigger scale. They have done it on a 1 megawatt scale, but not on a 10 or 100 gigawatt scale. It's going to take them another couple of years, but I think it has a lot of potential. This is where I see a lot of potential for the future in terms of power.
So you're presenting us really amazing examples, hard design, architecture design, and engineering is brought together. And that with the issue of urban planning in cities, in the future of cities. So given the fact that we don't have so much future work into new buildings rather than building stock and refurbishment, this is a different issue, isn't it? It's a very complex story to start planning as a sustainable city. Shows identity, culture, and all those aspects are part of it as well. But what's your opinion about having this design and engineering going together to consider this refurbishment task we're facing, which have stuff like heritage and other restrictions we're facing?
Yeah. No, I think let's say this is the biggest challenge we face in the Western world. Like in Eastern world, it's different. They still have. I saw a number that 200,000 people are moving into the major cities worldwide every day. So in 3 days, it's a city like Stuttgart they have to build. So there's still a huge demand for new buildings globally. But in the Western world, we always say like Germany is built already. And it's true. Austria is built. Like, there is always going to be a demand for a few buildings. But if we have to become carbon neutral, the entire building stock has to become carbon neutral by 2050. If politicians are really serious about this goal, this is going to change the face of our cities. This is going to change the face of our buildings. Our Vienna is going to look different. If you put 30 centimeters of foam on every single building, on every single heritage building. Yeah. So I don't have an answer. Honestly, I don't have an answer. I think like what we have done in Helsinki, showing the synergies, is one step. We also have to be smart about materials, what we can do with our building stock without changing the face of our buildings. And I think there are new materials which are performing really well. We need to think about this. Like glass has developed so much that we can do so much with glass these days. And it's not one solution. It's certainly not one solution. But because of exactly the question you have raised, we started to collaborate with several universities worldwide on something we call the Future City Lab, to really think about exactly this and how does mobility change our cities? Like, I talked to somebody at Audi who said to me, they have this urban design award or competition. They had 2 years ago, they're going to have another one this year. And he said, they believe that the car has changed our cities. Now the cities will change the car. That's what they believe. That's what car manufacturers believe these days. So, but this will mean that the cities will change. They will look different in 50 years. And I think the cities will adjust to it. The question is how, and I think you as architects, I'm not an architect, I'm an engineer, but in this collaboration we need to find answers that are smart, because otherwise some engineers come and they find solutions, but we're not going to have the cities we want to live in. Not that I want to blame my profession, but I think that's the risk. So better we find smart solutions so that we design solutions. And I also think there are, in this challenge, also with global warming, the cities, like microclimate in cities, urban heat island effect, etc., etc. There are so many opportunities, inherent opportunities. We really have to bring it together and we have to make it obvious and visual so that people understand it. It's like Bruce Mouse said, we don't want to have a park in a city, the city has to become a park. And I think this is really the way we need to approach it. And then, again, like looking at things like the ferries, looking at energy sources, how much we can generate, what we can do with new materials. And I think all together will provide us the solutions we need, but I don't have the answer. Yeah?
Have you ever done a case study in China for post-climate design with an architect?
Oh, we have done work in China. Is that enough? No, to be honest, I think it's not the market which we see as our primary target. It's more like if architects we do a lot of work with, if they come and say we have a project in China, we join the team and we have no hesitation to do it. But what we see right now in China is, and there are always exceptions, but there's a lot of development going on where the question is, how can, like in Shanghai, how can we design a district for 300,000 people which is built in 2 years? And then we come and say, oh, wait a minute, let's do some modeling first and see, and we can shift this. And the immediate reaction is, by the time you do your modeling, we have this thing done. And to a certain extent, we think we have to allow them to make their mistakes, to understand it. We still do mistakes. How can we blame people in China to do the same mistakes? And I think to a certain extent, we love to do work in North America because a lot of design we see from North America became the universal design. So sometimes we think maybe we can have a bigger impact if we can have a small impact on the North American market. If they become, because also like the big architecture firms, most of them come out of the US. SOM, HOK, and now there are these huge conglomerates like AECOM, 40,000 or 50,000 engineers. All of a sudden they figured out they have so many architects in their departments that they became the biggest architecture firm worldwide. Nobody knows them. They are doing the work in China. So we said, if we change, if we can have, like we do not change anything, but like a little bit of contribution to a change on the North American market, this might have a bigger impact of what's going to happen in places like China and India and other places in the world. And you know, as soon as the mentality changes in China, and if a client comes to us who tells us that he wants to have something really good, something smart, I think we are pretty open to work there. But right now we would not consider opening an office in China. That's not. I think for us, like unlike firms like AECOM, for us, revenue is not a goal. It's got the kind of work we are doing is the goal. Of course, everybody wants to make money on us. I'm not saying that we don't want to make money, but we don't have a target where we say we are 50 people now, in 2 years we want to be 200. That's not our target. We have a target that we say in 2 years we want to have so many good buildings done wherever, and making money on the side. So that's why China is not so interesting for us right now. It might come. Things change. We got a little interested, I have to say, in Korea. I think Korea could become really interesting. Okay, last question.
Just like just a cute idea. I remember 4 years back, I saw this one concept project by DARPA, you know, DARPA, the American military research branch, and this concept was a sort of small brace or something like that that were either in your hand or at least on the back of the neck, and the entire point was that it could cool the blood as it flowed through your body. I was just thinking about the amount of work that goes into the design and the construction of all of these buildings inside of very warm climates, when in the end it's just that everything acts upon each individual body. And I was thinking that there's this area where the comfort, the comfort goal, where it's focused on every individual, because everything becomes suddenly too much if each individual can just cool himself down in a small place. So in the end, it's all that it's happening. Building each body or warms it up.
We never studied it, but it could be
thing.
interesting for the future. Nobody knows. We still have individual cooling devices, like a small chiller around the neck. Who knows?
And then we go.
Yeah.
Thank you very much.
Okay, thank you.